Welcome to the Deep Dive, where we sift through the latest research to bring you the most important insights. Today, we're plunging into the pretty exciting world of large language models, LLMs, and specifically their ability to reason. I mean, you've seen them write poetry, generate code, answer complex questions, but how do we make them even smarter? Especially with logic, complex problem solving.
Yeah, that's really the frontier right now. And our mission today is to unpack a really groundbreaking new approach called TreeRL. We've got this fantastic new paper, TreeRL LLM Reinforcement Learning with On-Policy Tree Search. And we're going to explore how it, well, significantly pushes the boundaries of LLM reasoning. Get ready for some hopefully serious aha moments as we kind of pinpoint the really innovative ideas here, stuff that's making LLMs genuinely think, not just spit out text.
Okay, TreeRL. Sounds interesting. But before we dive right into that, maybe set the stage a bit. What are the specific reasoning challenges for LLMs, especially, compared to maybe more traditional AI? Like I'm thinking chess or Go.
Right. Good point. So traditional AI, especially in games like chess and go think AlphaZero, right? They've benefited hugely from combining something called tree search with reinforcement learning, RL. Basically, the AI explores tons of possible moves, looks down different paths, evaluates consequences, finds the best strategy. It's all about searching that decision tree, often really exhaustively.
And LLMs started showing some serious reasoning chops more recently, didn't they? Like 2022, 2023.
Oh, absolutely. Big leaps. And researchers naturally started applying RL techniques to LLMs. Often it was about learning from, self-exploration and getting feedback, maybe just whether the final answer was right or wrong. But here's the interesting bit. Well, tree search was this, like champion in traditional AI. Its full power wasn't really being used for on-policy RL training with LLMs.
Okay, hold on policy training. Can you unpack that a little for folks who aren't deep in the RL weeds? Why is that important here?
Sure. So on-policy basically means the model learns directly from the experiences it generates in real time as it's exploring. It's not just learning from some static data set collected beforehand. It's actively trying things, seeing what happens, and adjusting its strategy based on that specific exploration. This is super important because you want the LLM to learn from the very act of generating diverse reasoning paths. Now, people were using tree search sometimes maybe to make the LLM's answers better at inference time or to create data for offline training later, but not really integrating it directly into that live on-policy learning loop for the element itself.
Gotcha. So learning on the fly from its own attempts, what stopped people from just plugging tree search into that on-policy loop? What were the hurdles?
Yeah, there were basically two big ones. First, efficiency. Plain old Monte Carlo tree search, MCTS. It's not very efficient for these modern LLM inference engines. Think about things like VLM. They're built for speed, for generating lots of text in parallel. MCTS often needs many, many small step-by-step generations. It can be slow. And actually, research showed it could sometimes be less effective than just having the LLM generate, say, 5 complete answers independently and picking the best one, even for the same amount of compute time.
Right. So the standard tree search method just didn't play nicely with how LLMs generate text quickly.
Exactly. It wasn't a good fit. The second challenge was something called reward hacking. See, sometimes people try to train a separate model, a reward model, to judge how good the LLM's reasoning steps are, not just the final answer. But these reward models can have issues like distribution mismatch. The reward model might be trained on different kinds of reasoning steps than the LLM is currently generating, so its judgments are off. And worse, the LLM can learn to just, trick the reward model into giving it a high score without actually getting better at reasoning. That's reward hacking. And it was a serious roadblock for getting reliable feedback on the reasoning process itself during on-policy training.
Okay, so efficiency problems with old search methods and this tricky reward hacking issue if you try to judge the steps externally. How does TreeRL actually get around these?
Okay, this is where it gets really cool. TreeRL is designed specifically to tackle those two things head-on. It's a new RL framework that directly uses on-policy tree search. And it does this through two key innovations. Real clever stuff.
All right, let's hear them. Innovation number 1. You mentioned EP tree earlier.
Yep, EP tree stands for entropy-guided tree search. This is their smart search strategy. So instead of MCTS's kind of step-by-step or sometimes random branching, EP tree does something different. It strategically forks new branches, new lines of reasoning, specifically from the points where the LM is most uncertain in an existing path.
Uncertain? How does it know?
It measures the entropy of the probability distribution over the next possible token. High entropy means the model is like, I could go several ways here, not sure which is best. So if the LLM is working through, say, a math problem and it gets to a tricky calculation or logical step, EP-tree spots that high uncertainty and says, okay, right here, let's explore a few different options.
Ah, so it focuses the exploration where it's most needed? That sounds way more efficient.
It is. Remarkably so. The paper says EP-tree usually only needs about 2 iterations, 2 rounds of forking, to build a really diverse and useful reasoning tree. Compare that to potentially many, many steps in traditional MCTS. And the results back it up. Experiments show EP-tree generates more diverse, more effective reasoning paths. It achieves a better pass rate. That's the chance of getting at least one correct answer in the tree compared to just generating multiple independent chains or using MCTS, even when using similar rounds of computation.
Wow. And you mentioned they looked at where EP tree tends to fork.
Yeah, this is fascinating. It gives you a real peek under the hood. They found it often forks at mathematical operators like plus or minus signs. Makes sense, right? Calculation points. Also at logical words like and or transition words like since, but places where the reasoning takes a turn. And get this, even at self-reflection tokens, like wait, it's like the model literally pauses and thinks. And EP-tree catches that moment of uncertainty to explore alternatives.
That's incredible. It's like seeing the LLM's thought process and knowing exactly where it gets stuck or needs to reconsider. Okay, what's the second big innovation? You mentioned process supervision.
Right, on-policy process supervision. This directly tackles that reward hacking and distribution mismatch problem we talked about. The beauty of TreeRL is it doesn't need a separate reward model at all.
Oh, so how does it judge the intermediate steps then? How does it learn which path is better?
It cleverly uses the tree structure that EP-tree just built. It provides fine-grained feedback or supervision for every single intermediate step within that tree. Basically, each step gets assigned a credit based on its advantage. How much did this specific step help in ultimately reaching a correct solution within that tree?
Advantage. How's that calculated?
It's actually a mix, a weighted sum of 2 things.
Yeah.
First, there's the global advantage. This looks at the step's contribution to the overall success rate for that whole problem, considering all the paths explored in the tree. Kind of like asking, big picture, did taking this step make finding a correct final answer in this tree more likely?
Okay, the overall impact.
Exactly. And the second part is the local advantage. This is more immediate. It measures the improvement this step gives compared to the step right before it in that specific branch of the tree. So right here, right now, did this step make things better than the previous step?
Mm-hmm.
They mentioned this setup is related to a concept at RL called Generalized Advantage Estimation, or GAE, which is known to be a pretty robust way to estimate how good actions are.
Okay, so it's using both the immediate local improvement and the overall global contribution to judge each step. And this all comes directly from the tree the model generated itself.
Precisely, and that's why it's resistant to reward hacking and distribution mismatch. The model is learning from its own on-policy experience what actually worked or didn't work within the paths it explored. There's no external judge it can trick. It's a really elegant, self-contained system. They also do something smart. They downweight the rewards for steps that aren't the final step in a branch, non-leaf nodes, to avoid overfitting to common intermediate steps that might appear in many paths, but don't necessarily lead to success on their own.
That makes a lot of sense. It's learning from the consequences within its own exploration. Okay, sounds great in theory, but the proof's in the pudding, right? What did the experiments actually show? Did TreeRL deliver?
Oh yeah, it delivered. They tested on some really tough benchmarks, math reasoning like Math 500, OmniMath 500, even the AIM 2024 competition problems, and also code generation with Live Code Bench. They used solid base models like Quinn and GLM. And the results? Pretty clear cut. TreeRL consistently outperformed the baseline, which was ChainRL, that's RLL, using just independent multi-chain sampling, no fancy tree search, and also other methods like MCTS sampling.
Okay, so better final results. What about the learning process itself? Did it learn faster or more efficiently?
That's another key finding. So if you look at the training curves, TreeRL and ChainRL might start off kind of similar, but after about 100 training steps or so, TreeRL really starts to pull away. It shows much more consistent and significant improvement over time. This points to better prompt efficiency, meaning it learns more effectively from the same number of training problems, gets more bang for its buck, basically, which really highlights that learning from these richer, structured tree experiences is more powerful than just learning from independent, isolated attempts.
And they confirmed this with ablation studies, taking parts away to see what happens.
They did. They systematically tested versions without the entropy-based forking or with only global or only local advantage. And those studies confirmed it. Both the EP-tree search strategy and that combined global advantage calculation are really crucial for getting TreeRL's top performance. Each innovation pulls its weight.
Okay, so it's innovative, demonstrably better. Are there any downsides, limitations, areas they still need to work on?
Yeah, they're upfront about that. While it's very promising, there are limitations. A big one is still that inference infrastructure point we touched on earlier. Current LLM inference engines just aren't optimized for this kind of tree search yet. So even though EP-tree is algorithmically efficient, in practice right now, it can still be about, say, twice as slow as just doing simple multi-chain sampling for the same amount of compute, even though it finds better answers with that compute.
Right, so the hardware and software systems need to catch up to the algorithm a bit. Makes sense.
Exactly. It's an engineering challenge, more than a fundamental flaw in the idea. They also mention exciting future directions, like exploring even more sophisticated ways to extract process signals from the tree structure and figuring out the absolute best way to normalize those step-level rewards. These are active research areas.
Okay, so let's bring it home. What's the big takeaway here for us, for listeners interested in where AI is going? What does TreeRL really signify?
I think TreeRL is a really significant step towards teaching LLMs not just what the answer is, but how to think their way through a problem. It mirrors how humans often reason, right? Exploring possibilities, backtracking when uncertain, learning from missteps along the way. It's about building LLMs that are moving beyond being just, sophisticated pattern matchers or knowledge databases. They're becoming more like genuine problem solvers that can handle complex multi-step tasks more robustly.
Yeah, that focus on the process seems key. It makes me think this whole deep dive really underscores that the future isn't just about making LMs bigger. It's about finding smarter training methods, like TreeRL, that use more complex feedback and structures. So let me ask you, what really stands out to you from TreeRL? And where else could this kind of tree thinking, learning from the journey, not just the destination, make a difference in AI?
For me, it's that tight integration of the search process directly into the on-policy learning loop, using the tree itself for supervision. That feels really fundamental. As for where else, imagine applying this beyond math and code. Think about complex planning tasks, scientific discovery, maybe even creative writing where exploring different plot branches could be beneficial. Or even safety. An LLM that can explore potential failure modes in its own reasoning path might be inherently safer and more reliable. That ability to self-supervise the process is, I think, a really powerful concept going forward.
That's a great point. Lots of potential there. Well, this has been a fascinating look at TreeRL. Thanks for breaking it down. And thank you all for joining us on this deep dive into the cutting edge of LLM reasoning. We hope you feel a bit more informed, maybe a bit more curious. Until next time, keep exploring.